So it's interesting that we have 3 language creators, and we have one guy who wrote a couple of books right before languages exploded. I think it's partially the reason that the languages exploded in the United States. That's Dave Thomas. So give these guys a hand. So, as we said a few minutes ago, the purpose of this talk is to basically understand from the language designers themselves how people build languages that people are passionate about. I think that one of the things that's often critical for me as a programmer is how I'm able to organize ideas in the language of my choice. And I think that before we get the perspective of the language creators, I'd like to get the perspective of a programmer.
Yeah, I'm the official parasite. I got my. Oh, I see. Yeah, sorry. Yeah, so I'm the official parasite on the panel here because I get to use all of these good people's work, for which I thank them all very much. So the question was, how do I organize my thoughts? And the answer is, I don't necessarily. What I do instead is that I try to use languages that do that for me, or at least lead me in particular directions. And for me, the choice of a language is one that has the lowest impedance from where I am to where I want to be. And all the languages that I love have that facility, they have that sense to them, that they actually help lead me through the organization and the choices that I make. And so, for example, when I talk about elixir and transformation, it leads me to think in terms of transforming as opposed to commanding. So that's the basis, I think, of everything I do.
And Joe, when we were talking about Erlang, when I interviewed you for 7 languages in 7 weeks, one of the things that you said was that Erlang might be more object-oriented than object-oriented languges.
No, it's the only object-oriented. That's right. It's the only object-oriented language. But that wasn't the question. The question was, how do I organize my thoughts and so on. And I don't know. I haven't a clue. I mean, it's a mess, basically.
Well, you have your little book here.
I have it. Yeah. Well, yes. I have my little book, writing. One thing I do is I write. When ideas are unclear, I try to write them down. And writing has 2 benefits. Once you've written it down, you've removed this clutter from your head, so you don't need to think about it anymore. And I think of it the kind of process of producing a book, because when you've produced it, when I worked with Dave and did the Erlang book, what I deliver are 12 XML files or 15 XML files, 1 per chapter and a load of stuff. The directory structure is a total mess before that, But what you get are my mess isn't checked into your archive. You just see the result. And how I get to that is a complete mess. And after it's all over, I just throw them all away. I don't check them into GitHub. I want to see all the failed stuff. I just throw it all away then. And then I've got the final bit. And then I read that later. And so I find writing clears my head.
Actually, but the other key thing there is throwing things away clears your head.
Absolutely,
and
yes.
I think
yes.
That's really important.
Because I can throw things away once I've written it down properly. And then the second thing I do is, the other way is, I remember I worked in the computer science lab at Ericsson. And whenever I got stuck, I went in there, and Nabil El-Shiri, he was been there a bit longer than me. And I'd go into his office and say, when I had a problem, I'd go into Nabil's office and say, I've got a problem, I don't understand this problem. And Nabil would always do exactly the same thing. He would go up to the whiteboard and he would draw a square, and he would draw an arrow going into it, and he'd draw an arrow going out, and he'd write the word in on the arrow going in, and he'd write the word out on the arrow going out, and he would say, a program is a black box. It has inputs, and he would point to the inputs. And then he would say, it has outputs. And then he would say, what are the inputs to your program? And I would go, something or other. And then he would say, what are the outputs to your program? And I would say something. And then he would say, and what is the relationship between the inputs and the outputs? And I would say, it's. And at some point in that conversation, I would suddenly rush out and go, Nabil, you're a genius! And I would rush out of the room. So I think this thinking about what the inputs and what the outputs are and what the relationship is. And when you can't program or you can't do things because you don't understand the problem. So you have to think and you have to write it down.
So it just struck me that we basically described the function.
Yeah.
Which was kind of the guy, a great setup for John.
You're writing stuff, but you don't know what you're writing.
Yes, so
But you don't realise that.
I thought I would answer this question by talking about how I like to organize and come up with code. And what I like to do is identify some hard problem that I want to solve, and then look for a small API of combining forms that will enable me to solve it. And a really great example is the pretty printing operations that I talked about this morning. So there, an important first step using Haskell is to invent the types of the API. So just coming up with the types is a very helpful start. And then the next question for me is, what is the semantics of these operations going to be? And I find it quite helpful to define a completely inefficient implementation, just to pin down the semantics. So for example, those documents I was talking about, I started off using a list of possible layouts. You can't implement it that way. They get exponentially large, but you can get your thoughts clear and understand the semantics that way. Once I've got the semantics, or an idea for the semantics of the API, then I want to know what are the laws that they satisfy. And I'll try and formulate those, see which ones are true. When I developed the pretty printing combinations, I didn't have quick check, but nowadays I would, of course, write down the laws, test them with quick check, make sure they really hold for the semantics. If they don't, fix the semantics probably. And then finally, use the semantics to derive an efficient implementation. And that paper that I referred to this morning, that's not really about the pretty printing functions. It's about this process that I've just sketched, going through the design by thinking about the semantics.
Yeah, I guess it strikes me that that's also the Haskell way, right?
Yes.
So we've got this lazy thing where you basically describe the world first, and then you draw a box around all the infinite possibilities to limit your outputs to something interesting. Yeah. And so Evan, as you worked on Elm, one of the things that you've done to help your readers actually, or your users approach functional languages, is to kind of put a box around the features that you have in the language itself, right? Could you talk about that a little bit?
Yeah, so I'm sort of benefiting from lots of great work. So like I do most of my programming in Haskell, and so before that was using standard ML and Campbell. So sort of once I started using languages like this, I found that you're sort of pushed into a process that has good results. You first have to say like, what am I even doing here, right? Like what would it mean to talk about the data that I'm working with? And sort of once you sort of understand what you're working with, doing stuff with it becomes crazily easier. So a lot of my work is also more library focused and language focused, which isn't quite the same as what my users are doing. So my process for writing code may not be helpful for everyone. It's more library creation. In that realm, you really do want to start like, what is the essence of the thing you're working on? So one of my coworkers is working on a thing called Elm CSS, where he wants to represent CSS in a way where he can generate stuff. And he's sort of coming at it from a more JavaScript-y perspective, which is how can I make my API look nice, and like what tricks are available to me such that my API seems nice, seems minimal. And then do whatever hacks you need to do to achieve that API. And sort of what I do, and I think what Haskell and Elm and all these sort of type of functional languages encourage you to do is start it from the other direction. Say like, what would it mean to represent CSS? And sort of from that, the answer kind of falls out. And I think once you sort of get used to this process, you can see what answer happened to fall out this time and be like pleased or displeased. So a lot of my process will be like, all right, here's my understanding of the problem. Let me see what comes from that. And I'll be like, unsatisfying. I'm not like proud to show this to someone. And then you do another revision. Okay, maybe I didn't understand the problem quite right. Maybe I can tweak it a little bit. Does that kind of match your?
Yeah, very
Yeah.
much.
And really, I think that comes from the language. And I don't know. As someone who like didn't create that framework, it's been really valuable. I don't know if you can speak to the extent to which that was sort of in the ether or.
So I think that's the kind of software development that all of us working on Haskell were interested in doing. And maybe it wasn't an explicit goal to support that well, but if Haskell hadn't supported that well, then we wouldn't have been happy with it. So it was an implicit goal, I think.
I also want to mention that writing things down is hugely important, especially when I'm doing JavaScript stuff. I recently did a rewrite of the virtual DOM implementation, which is how we make rendering work really quickly. And I just got to a point where in the JavaScript I realized like everything was wrong. Like the fundamental the fundamental model that I was working with just like wasn't gonna work. And like basically I was gonna have to refactor a bunch, but in JavaScript it just was like, well, what is that? What does that do?
RM minus RF is.
Yeah, so like I just was sitting there like, oh my god, it's all garbage. It's all throw it all away. And so instead of just continuing this sort of like bad habit that I have, I think, especially in JavaScript, of just like barreling on and hoping that it's going to be nice eventually. I mean, often that can work. In this case, I hit this barrier where I was like, okay, this is just broken. And so I went to a notebook and sort of said, okay, what does it really mean to patch my virtual DOM? Okay, it's this. And it's exactly the process I would have done in Haskell, in Elm, in one of these languages, because you have to say what is my data as opposed to inventing it haphazardly as you go through.
That's really cool. I mean, so we just heard Evan say that, well, sometimes I'll plow on before things are beautiful and not perfect. And that's not my experience with your software at all. My experience with your software is that you are not satisfied until it's beautiful. So a lot of us talk to people about the things that we've built with code, and we've asked those people, how do you make this thing beautiful? Well, Evan does the same thing with the Elm language, right? So you think of usability. So actually, there's a question on their syllabus or the program that said, how do you think about usability when you design your language?
So yeah, I think this is informed a lot by my own personal struggles to learn languages that I love, right? So my process sort of was starting with Java, doing some C, seeing PHP and being like, oh God, I'm glad this is only a week of coursework. And then doing a lot of Scheme, getting into OCaml, getting into Standard ML, finally getting into Haskell. And so I was very lucky in that I had great instructors all along that route, but things were still difficult, particularly when I made the transition from OCaml to Haskell. And I made a couple mistakes making that transition, but there were certain concepts that I struggled a lot with, and when I finally understood them, I was frustrated that they were simple, and I felt that something had gone wrong, that I had to work so hard or like be confused in this way. And I also had this feeling that like, I think I'm pretty smart. Like, why is this so hard? There was this sort of gut feeling that the essential piece here could be sort of presented in a way that was more accessible. And that's really what's driven a lot of work on Elm, is this just like, how can I, as quickly as possible, get people to see the beautiful thing that just was there before me, that for some reason wasn't cool or wasn't sort of catching on.
Yeah, that's an amazing way to say it, and it's interesting to see the back and forth, as you're sharing the story and looking at John and recognizing that a lot of the the Haskell leadership came right here, and I wanted to ask you, John, nothing says beautiful like designed and committed, right? So how did Haskell survive that?
Yeah, so I think one thing that is quite important is that although there were many language designers and language implementers on the Haskell committee, we were explicitly not trying to, kind of fit together everybody's language so that it would be as easy as possible to just adapt the front end of everybody's compiler. So it wasn't the case that everybody had their feature that they wanted to get in and we kind of stuffed everything into a box. Rather, we started with a clean slate. And I think that was important. The other thing that I think probably helped was that all of us were, we were working in university research groups, and all of us were teaching functional programming to students. We were all enthusiastic about that. So one thing that was in our minds the whole time was, is this going to support the kind of ideas that I want to teach? Am I going to be able to teach these features to my students? I think that's a good perspective to have. That, it makes you want to avoid unnecessary complexity and keep stuff simple enough that you can teach it.
Hey, Bruce.
As an outsider, my theory would have been that by committing to purity, there's only so wrong you could have gone. Like the craziness couldn't have gotten so out of hand. How does that hold up to?
You went on the Haskell committee.
Okay, I'm curious to know.
There were a number of fairly crazy ideas that we discussed.
What kind of stuff?
Well, one of them was the semantics of pattern matching. So if you got a number of function clauses, then in Haskell today, you match them, you try them from top to bottom, and you match each one from left to right. And that order really matters because of lazy evaluation. So, the order in which you match the pattern drives the evaluation of the arguments. And it might be that, if you evaluate them in a different order, then a function call will raise an exception instead of returning a result.
Yeah. And for some context, OCaml, because it's not lazy, doesn't have to be super strict about its ordering. It can do sort of trickier testing.
That's right.
Elm actually does trickier testing as well, because we can, I guess.
Yeah, in a strict language you can. So there was a proposal in Haskell that we should adopt a pattern matching order that would be determined by the compiler, fairly hard to predict, and support parallel matching. And so there was quite a complex proposal for what pattern matching should mean.
Yeah.
And this is one of the contributions that I made. I said, we can't do this. It doesn't have a compositional semantics. And then other people in the committee said, well, we just haven't thought of the compositional semantics yet. Go home, John, and think of it. So I spent an awful evening, or maybe a whole weekend, trying to come up with a semantics for this complicated mechanism that we were going to introduce. And when I came back, I said, it just can't be done. And luckily, I had enough credibility on that point that we decided we would drop it, and we kept with a simple top to bottom, left to right instead.
Was the trouble mixing laziness with the parallel matching?
Could
or
you talk into the mic so the
sure.
people?
Yeah. What was the trouble mixing parallel evaluation with laziness, or was it something else? Just for my own personal.
So the problem was that there's no really well-defined, unique order in which you might want to match. So you get a rather complicated order, you maybe wouldn't be able to predict it, and that would affect the meaning of your program. So you would
laziness.
With laziness,
Okay.
yes. Laziness is a key element here. If you don't have laziness, you don't have this problem.
Gotcha.
But we had laziness, we knew that. So and that's just one of the things. There were a number of things that came up that never survived to see the light of day, thank God.
So a couple of points occurred while you guys were talking that was kind of implicit in what you were saying, but to me is incredibly important as a consumer of the stuff you're producing. And I'd be very interested to know for all three of you guys just how much you think about this as you're doing it, and to what extent it's simply a byproduct of all the other things you're thinking. And that is, for me, a programming language is a way that I express myself, right? At a very deep level, because it's a very personal thing, right?
Yeah.
To some extent, my success or failure depends on my ability to communicate, both to the machine, but also to other people through these languages. So I value the ability to express myself in the languages that you create. To what extent then, because you kind of touched on that indirectly before you went down the lazy rabbit hole, to what extent do you actually think about that? To what extent do you think about not just the purity? Because sometimes expressiveness involves ambiguity, right? And expressiveness involves not being pure, but giving people a choice as to how they say something, because that choice indicates what they're thinking about that thing. To what extent do you think about that when you're creating a language? Maybe give Joe a turn first. What do you think?
Can I? Yeah, you think about it a lot, actually, because you're creating ways of thinking. I always think programming language design is actually philosophers, because this is sort of practical philosophy. We are creating things that influence how people think, and that's what a philosopher does. But I want to go back to your question. So, because Erlang's different to Haskell and things in that sense.
Yeah.
And I started work on that in 1985 at Ericsson. And our job there was to try and make something that's fault tolerant. And to me, the stuff should not just fail. So the first observation about that was you can't do it on one computer. You cannot make a fault tolerant system on one computer just because the entire computer might crash. So you need two computers. At least, I mean, you could have 100 computers, but, and that means if one computer might crash, you can't have shared data structures. And if you've got two computers, it means it is concurrent. And if you've got two computers, it is parallel. And if you've got two computers, you can't break the laws of physics. Because I used to be a physicist, right? So here's the starting point. And wait a moment, it is parallel. And wait a moment, the world is parallel. And the world does consist of millions of things all working away in parallel. And Carl Hughes sort of coined this term physics programming. So I had this, because I was a physicist, and I said, don't break the laws of physics. And then I see all these programming languages which break the laws of physics every day. They two-phase commit doesn't mean to say you've got the same data in two different places. Right. It means you don't know it's changed yet. I mean, it's absolutely absurd. So there are some fundamental truths. You don't know how it is now, you know how it was the last time you told me. That's not how it is now. And so I thought, hang on, let's make languages which accurately reflect reality. And then I thought, well, hang on, this is the fundamentals of this is messaging. I mean, I remember thinking, I loved email. Email's great. You can send email to anybody. And I was thinking, at one stage I thought, so why can't you send email to everything? So how would you write I remember thinking, I had to write a room booking system for Ericsson. And you thought, wait a moment, the obvious answer is you send email to the room, and it knows when it's booked. You don't put it in a database. And that's not breaking the laws of physics, because there's not going to be simultaneous information in two places. And unfortunately, you can't send email to a room. Yeah, but wait a moment, the Internet of Things, you will send email to a room. And that's actually called object-oriented programming, where you send messages to things. And it's the actor model that Carl Hughes came up with. Yeah. And you're not breaking the laws of physics. And the world is parallel. And suddenly we've made a programming language that's a parallel, concurrent programming language. And it's in this funny thing, because the world is parallel. We're programming parallel problems. And yet everybody's doing it in sequential languages. And then you get this artificial difficulty. Because you've chosen the wrong paradigm, it becomes artificially difficult. And then we're very acutely aware of the combining forms. In our case, it was the process and the link. Those were the combining forms from which you could build everything else. And that took 4 or 5 years to get right. And we tried umpteen different ones and threw them away because they didn't combine properly. No. So I had the guiding thing, don't break the laws of physics. And write parallel programs from the start, because the world is parallel. So it's not like lazy evaluation or maths or that's how the world is. Right. Rays of light and sound. Sorry. Oh, and I had to answer your question, didn't I? Which I said I'd answer but now I've forgotten what it was. So
Give them a right, give
I'm
them.
gonna step in here. for a second.
What did you ask?
Do you think
What's up?
about communication?
Sure.
So it seems to me sort of that in neither the case of Erlang or Haskell was it necessarily that someone sat down and said things need to be immutable. People sat down and said other things that implied things had to be immutable. Is that a fair thing to say? In that once, if you're in a setting where you have laziness and mutation, like things are going to be bad. But the driving force was laziness. And with Erlang as well, is it true that...
That's not really true.
Okay.
So Haskell was designed to kind of unite the work in lazy functional programming, all of which was with pure immutable languages. So that was a given from the word go.
Right. But the motivation wasn't, I think immutability is good, but it was, I think laziness is interesting.
I think the motivation was immutability is good and laziness is interesting.
Okay. Yeah.
You didn't like the answer.
Well, but...
He gave you the answer. You didn't like the answer.
Well, so in some ways, it feels like a lot of languages made in the past couple of years sort of just look at laziness as a tool for reliability, right? So in a lot of ways, all Elm values are immutable, but it's because I've experienced what it's like to program in that way, and it's really nice. And I don't know, I would have liked the story to have been that by thinking about effects and like interleaving of effects, you're sort of put on this road in a way that maybe wasn't really the intent. It was this question of how do you start interleaving things, and that sort of necessarily puts you in a place where your data is immutable. But yes, that's wrong.
So I think, of course, in a sense, you're right. If you have lazy evaluation and you have mutation going on,
You also have a bad language.
then you're screwed, basically.
Yeah.
You're not going to be able to predict when mutation happens. So that you are forced to be pure if you have a lazy
Yeah.
programming language. And of course, it might have been tempting, I suppose, because everybody needs mutation now and then. So it might have been tempting just to have snuck it into Haskell as it snuck into ML.
Well, did it sneak in?
Did it sneak into ML? There is
Yeah,
mutation in ML.
I don't know what the timeline was, though. My understanding was that was sort of a core piece of
Yeah,
the
okay,
design.
so references and mutation were in ML from the start. But they're there, you can't tell from the type of an ML function whether it has side effects or not.
Right.
It might have been tempting to have treated it in the same way in Haskell, except that lazy evaluation would have made that nuts.
Right.
Just one second. Let's bring this down a little bit. So I'd like to ask Dave. So Dave's on the panel because he's basically seen two languages explode before they were going to explode. Some might argue that that the second one exploded because Dave started writing about it. He'd never claimed that. I absolutely think it's true. But I have a question for you, Dave. What did you see really early on that tipped you off that these languages were special?
So, with Ruby, all that was special is I liked it, honestly. And out of all of the languages I had been using up until that point, it had the right combination of, it made me happy. You know, it had the right combination of features. It wasn't overly strict. It wasn't overly sloppy. It just kind of like, it was comfortable, you know. And to be honest, it was something where I really, really loved it, but also didn't trust it. It felt too lax at times. And it took me a year or two to get comfortable with it. The second of those years was spent writing the book, so I got very comfortable with it. But I wouldn't have done that had I not got some degree of, yes, this is good, this is right. The actual story, though, is kind of like not quite as ideal as that, because it started out because Andy and I came across Ruby, and I really loved it. We wanted to write a book on active specifications, which nowadays would have been called RSpec or something, but and we needed a language that let us express requirements, if you like, in a language. And the metaprogramming in Ruby would let us do that. So we started writing that book, and we discovered we were writing more about Ruby than we were about what we wanted to write about. And so we kind of like gave in to the inevitable and just changed the book around and wrote about Ruby, and that's how it came out. Elixir was different. I'd been looking for a language for many years, maybe 10 years, that would allow me to talk about transformative programming. Right? And I've got to be very careful what I say, so I'm not that far away from people that I might offend by mistake. I found it difficult to, I liked Haskell, but I didn't feel I could use it as a basis to explain to the average working programmer. And that was a failure on my part, and I didn't know really how to express the ideas in a kind of clear enough way to popularize it. With Elixir, I came across something that had many of the features that I wanted, not all, but many of the features I wanted, wrapped on top of a fantastic virtual machine, which meant it actually had some benefit. It wasn't just an academic language, it was actually a language where I could sit there and switch whatever, 2 million requests a second or something. So it had a lot of benefits. And because of that, I just felt this was right. This would actually lead it. At the same time, it's pretty clear to everybody that the world is becoming functional. That the old ways they're not working. Right? I mean, Moore's law has not stopped, but it's changed. Right? And we're no longer just throwing MIPS at something. And so we have to find different ways of making these things work. And so it's just a sweet spot, just a perfect storm of all these different things that just attracted me. Added to which, I mean, the community, Jose, and now everybody else, is just so nice to work with.
Yeah.
That made it a pleasure.
So Joe, we've talked a lot about the functional languages. Erlang was one of the early commercially successful functional languages, but it didn't take the approach that everyone else did. Took an approach that was much more concurrent, based on the beam that had the error channels baked in from the ground up. So why do you think that people are so passionate about the Erlang language?
Because the programs just work. and it's because they're not breaking the laws of physics. And Ulf Fiege, he said to me one day, he said, it's the funny thing about Erlang, why did we just write these, they just work. Do you remember? And then he asked me why. And I thought, it's to do with concurrency and modeling things. So in the first Erlang book, I came up with, it's still my favorite example of a lift control system. And in the book, there are 3 lifts.
Elevator.
What are they? There are 3 elevators and 10 floors. And I want to describe an algorithm that schedules a lift. And I thought, so how do you do this? So you say assume each lift doesn't know elevator, doesn't know about the other ones.
I'll do the sign language of the site.
Okay, right, you do the sign language. I'll just call them lifts. Are you okay with me calling them lifts? Yeah, good, right. So just assume each lift has a stop list. So it knows where it's going to go. It knows if it's going up or down, because it's not going to suddenly change direction. Right. And it's got a stop list. And each floor is a process, And so when you press the up button, you send a message. You send a message to each lift, to all 3 of them, and you say, how long is it going to take you to get to me with your stop list? And they compute that, and they send the answer back, and then you choose the minimum, and say reserve that one, and you send you do the temporary, how long is it going to take? And the next message you send back is you send to one of them, stop on my floor, and to the other 2, you send, forget it, right? Now, if you model that, you would say, how many processes do you need? The answer is 13, 3 lifts and 10 floors, right? It cannot be any other number. It must be that. And the algorithm is completely trivial and really easy to explain to anybody and really easy to understand. And I never saw that in object modeling. I never saw these, if there are cars and bikes, a class of wheeled objects, and goodness gracious, is it a... And I've never seen, but physical modeling, when you observe the universe and you write down, if we were modeling this panel, well, there are 5 concurrent processes in it. If we're modeling you, there are as many processes as there are people. and we have no trouble understanding this. We don't have a common memory. We don't have a shared memory. We've each got an individual memory, and we send messages, and we might not listen, and we might miss them. So if you program it just like that, it just works because that's how the universe works.
Yes.
And if you program it in any other way, you will get artificial difficulties. And if you program it in a sequential language, you will run into problems. And if you program it in Node.js, your brain will melt.
He did it. He got it straight, Bruce.
Don't mention the Node.js.
So you heard it here first that God codes in Erlang.
Or
The lambda calculus.
So the question is, what do people love about Haskell, right?
Yes.
So I think there are 4 things. One thing is the notation. People often say Haskell is a very beautiful language.
Yes.
It's very concise, very elegant, and powerful. Something else that I think people love is purity. When you state a law in Haskell, it's true. When you state a law in Erlang or ML, you often have to mumble into your beard a little bit, you know. It's true,
I don't have a beard, John.
provided there are no side effects. But when you state a law in Haskell, it's true. No ifs, no buts, provided you don't use unsafe performance. But that mumble is a much less important mumble.
What about the strictness annotations to make it work?
It doesn't matter. Oh, well.
panel.
So people really like the purity, I think, because it gives you much more confidence in using those laws and reasoning about your code. Something else that people really love is the type system. So people often say, once it type checks, it just works. There are even T-shirts you can get that say, it type checks, ship it, which is maybe a little extreme. And you can see this because the type system has been extended further and further and further to make it more and more possible to capture what your code is really supposed to do in the types. Simon Peyton-Jones says, adding things to the type system is like throwing red meat to hyenas. People just pounce on this stuff, and they really want to use it. So that's something that people love. And I think, finally, one thing that I would think people love is using Quick Check for testing. The Haskell Quick Check is very powerful. If you look at the packages on Hackage, it's by far the dominant testing tool. There is an HUnit library, but it's used about half as much as Quick Check is. So that's something that has really been adopted very strongly in the Haskell community.
Oh, it's amazing. So Evan, when I wrote about Elm in the 7.1 languages, that's the language that people kind of light up when they see in the book. And so in a very short time, you've got this following of fanatics, and that kind of goes back to the beauty of the language. What is it about Elm?
So I think at the root is this, like, you feel good when you write a program. And I think that's sort of the connecting thing that like, sort of independent of the particular details, there are things that like make you feel good about what's going on. And so essentially a lot of the things that are nice about Elm are what John said, but I would say them different, right? And I think one of the crucial things that's important and why people really get into Elm is because I say it's slightly different. So a lot of the emphasis is sort of recognizing that, over the past, I don't know how many decades, we've developed a way of writing programs, whether that's in Haskell or in OCaml or standard ML or sort of the precursors to those things. That's really pleasant. And so what Elm is about is finding that essence and like not trying to be too creative outside of that, right? Like what was the core part that made it really, really special? And then just saying no to basically everything else. So the longer I work on Elm, sort of the more I feel that just the basic feature is algebraic data types, just like the ability to think about and model data in a nice way. And I think really sort of emphasizing those things, because I think we forget how great like how crucial that is. You know, there's so many other pieces that are amazing and pleasant and nice that we forget that we can, like 90% of programmers will have their minds blown by using algebraic data types. And I think at least what I've been trying to do with Elm is sort of get that joy that I felt learning languages like Haskell and make it so people aren't afraid to go down that route, you know, as if it's dangerous. It's like, well, what's going to happen? I don't know. But yeah, so.
Yeah. Guys, let's give these guys a hand. This has been an amazing panel.